Alright, graph and calculator problem. A cardboard sheet that measures 21 inches by 56 inches has its corners cut out and is then folded up into an open box. Let's draw a diagram. So here is our rectangular sheet. It was 21 inches by 56. So there's a 56, there's a 21. Okay, but we were cutting out its corners and folding it up into an open box. And so we're going to be cutting out a square, noted right there, from each corner. So we're going to cut out a little square there, a little square there, square, and square. Because then we'll be able to fold up those sides to make an open-topped box. And what we're saying is we're labeling that distance x. All of those are x's on all of those pieces, and they're squares, so both sides are x's all over that thing. So we want to find an equation for the volume of the box in terms of x, the side length of the square cut out of each corner. Alright, so think about what is left when we've cut out the corners. We're left with something like that. It's not a perfect drawing, but that's the idea. Something like that right there. So what would that bottom piece be? Well, notice we're cutting out an x here, that's an x, and we're cutting out an x there. So we're cutting out 2x from that 56. So that side would be 56 minus that 2x. Similarly, up here, we're cutting out an x there and an x there. So what's left has to be that original 21 minus that 2x. Okay, let's draw a three-dimensional representation of this. If I folded this box up, I'd be looking at something like this, where here is my 21 minus 2x length, here is my 56 minus 2x length, and how tall is that box? Well, if that is a side, essentially, that's the height, and we know that that is x, and so that height has to be x. So if we want an equation for the volume of this box, it's a rectangular prism, which means length times width times height. So the volume has to equal the length times the width times the height. So let's say x times 21 minus 2x times 56 minus 2x. And we want to know what is the domain in the context of the problem. Well, let's look at this diagram. Think about what's happening here. As we increase the size of x, the length of these sides there is going to get smaller and smaller and smaller. And we can only make that smaller for so long because it needs to have an actual length for this to make any sense. And so we can think about that 21 minus 2x, and we need to make sure that 21 minus 2x is greater than 0. Because it wouldn't make sense if it didn't have any length. We would have essentially gotten rid of all the box. So let's solve this. So 21 is greater than 2x divided by 2. 21 halves is greater than x. 21 halves, what is that? 10 and a half? So 10.5. We know that x has to be less than 10.5. So our domain is going to be all x values in the interval going from 0 up to 10.5. And I'm not including those numbers because it doesn't really make sense to include them, because then we'd be dealing with like infinitely thin dimensions, and that doesn't make sense. So what corner cut size will result in a volume of 2,000 inches cubed? Well, that's asking the question. Volume is 2,000, and we know our volume equation is x times 21 minus 2x times 56 minus 2x. And so to graph this, we're going to graph this equation on our calculator. So let's start there. Let's graph our polynomial, x times 21 minus 2x times 56 minus 2x. And then let's graph the horizontal line, y equals 2,000. So let's talk about how we graph this. Well, first off, we're graphing that first equation, which is y equals x times 21 minus 2x times 56 minus 2x, and type it in just like that. But we need to adjust our window, so hit the window button. X min should be 0, X max should be 10.5, the domain we found. This will give us a perfect window, 0 to 10.5, then zoom fit is option 0. Graph the line y equals 2,000, and you should see something that looks pretty much exactly like this. And so we're finding these two intersection points. It's going to tell us the two x values that give us the volume of 2,000. And so to find those, we have to second calculate the intersection point. So first curve is the polynomial. Second curve is our horizontal line. And let's guess that first one is maybe around 3 or so. And our calculator tells us that the intersection is when x equals 2.419. I'm rounding 2.4185. And let's go second calculate, intersect again to find our next one. First curve, second curve. Let's move our cursor over closer to the other one, so maybe that's closer to around 6. And our calculator tells us x equals 7.144. So what do these numbers represent? These are the x values, which are inches. The inches that we would cut out, two different options for the length of the inches we cut out, square in that corner, that would give us a volume of 2,000 cubic inches. Cool. All right, well, what corner cut size will maximize the volume, and what is the maximum volume? Well, we need to find that maximum. So we have our graph, so second calculate maximum is option 4. Left bound, 0. Right bound, 10.5. Guess, just hit enter. It'll take us straight to that maximum, and it tells us 4.666, comma, 2,540.741. So what corner cut size will maximize the volume? Well, that's going to be 4 2/3 inches. Will maximize the volume, and the maximum volume is 2,540.741 cubic inches. I wrote centimeters, cubic inches, so let's say inches cubed, just like that.